Hello and welcome to another lecture of classical motion of a single particle. In this lecture, we continue our previous discussion on simple harmonic oscillators under different effects. So, for example, we already have seen that how a simple harmonic oscillator oscillates whether there is neither any energy source or any energy sink, and then we actually discussed the case for a forcing where you are giving energy or injecting energy to the system to an oscillator in a periodic manner. We said this is very interesting in nature and especially for the physicists, because it corresponds to very realistic cases and models. Okay. Then we also discussed the case where an oscillator is subject to some drag force when the oscillator oscillates in a medium and the medium is giving some friction type of force which opposes the motion of the oscillator. And we said that although this is not really belonging to a pure classical mechanics case, because there is a heat which is getting dissipated and you have to take thermodynamics into account, but we can, for the sake of simplicity, if the relative velocity of the oscillator and the medium is moderate enough, then we can model this effective dissipative force to be proportional to the relative velocity between the oscillator and the medium. Okay. If you are now sitting in the reference frame of the medium, then you can actually, although I have not introduced the reference frame, I can simply say that if you just, but you all know what relative velocity is. So, we can simply see that if the relative velocity of the oscillator is moderate enough, then we can model the friction force to be proportional to the velocity or the relative velocity of the oscillator. After that, we discussed, we digressed a bit and we discussed the general nature of motion of a particle under a simple harmonic potential. And then we also showed that in this case every motion, every possible motion is a bounded motion and the orbit will be given by an ellipse. Okay. Today, we will again start a little bit of recapitulation of the damped harmonic oscillator, and then as promised I will go to the case where we will consider both the forcing and damping simultaneously. Before that, just giving you a formal recapitulation of what we have already discussed in the case of a harmonic oscillator. So, for the free oscillation case, the equation of dynamics is given by this x double dot plus omega 0 square x is equal to 0. Okay. Now, we know that omega 0 is the natural frequency of the oscillator. Okay. And the solution is given simply by this x t, which is equal to a times cos omega 0 t plus alpha. Okay. So, alpha is the initial phase, omega 0 is the natural frequency, a is the amplitude. Then if the oscillator is subject to a periodic force, okay, of amplitude f and with a frequency gamma and an initial phase beta, then the resulting equation is given by x double dot plus omega 0 square x is equal to f by m cos gamma t plus beta, which is no longer a homogeneous equation, and then we have to consider the case for a particular integral and a complementary function. Okay. And your total solution will be a superposition of those two. So, this is the complementary function which is the solution of the homogeneous part, that means when this force part is 0, and this is the particular integral which is the solution for the non-homogeneous equation. Okay. And then you see that there also we distinguished two cases. The first case is the gamma not equal to omega 0, that means the periodic force frequency is not equal to the natural frequency of the system, and there we had a solution which is x is equal to a cos omega 0 t plus alpha plus f by m omega square minus gamma square times cos gamma t plus beta, and we saw that this particular integral actually is in phase with the periodic force which is acting on the oscillator. Okay. But this type of equation does not hold good when your omega is equal to gamma. So, I just correct here a little bit. So, this should be omega 0 actually, and then Again you see when omega 0 is equal to gamma, then we have to find a new type of solution which is much more feasible and does not blow up, and we call this is the case for resonance. Okay. So, we can write this. So, this is the case of resonance. Okay. And here you can actually show that again your equation is composed of two parts. One is the complementary function, and which looks like simply a simple harmonic oscillation, plus another sinusoidal function, okay, a trigonometric oscillatory function, okay, with the same frequency and initial phase as that of the periodic force acting on the oscillator, but now it is multiplied or modulated by a linear function t. Okay. And you see that also there is a pi by 2 or 90-degree phase shift of this particular integral with respect to the periodic force which is acting on the particle or the oscillator. Okay. So, that we already have discussed. When we discuss the case for oscillation without force, but with some damping, then the equation is given by x is equal to a e to the power minus lambda minus root over lambda square minus omega 0 square times t plus beta e to the power minus lambda plus lambda square minus omega square under root over times t. Okay. So, you see that you have again an equation which is homogeneous. So, you do not have the problem of finding the particular integral and the complementary function, okay, but you can simply now have second order ordinary homogeneous equation, okay, ordinary differential equation, but now you have a new term which is x dot, and we said that if we can now distinguish three cases where lambda is less than omega 0, this is the first case, okay. We call that the case of underdamped oscillation. Then this one was the case for overdamped oscillation, and this one we called where, so overdamped means your lambda should be greater than omega 0, that means the damping coefficient is greater than the natural frequency, but when these two are equal, then we have a critically damped situation. Critically damped oscillation. Okay. And we found exactly that whenever you have an underdamped case, then the resulting equation should look like some x t will be equal to some amplitude a e to the power minus lambda t times cos, okay, I can write like this, cos omega dt plus some alpha, okay, where omega d is nothing but root over lambda square minus omega 0 square. Here omega is greater, so it should be this. I have to check actually which symbol I used over here. So, I used omega d for, yes, omega d for omega 0 square minus lambda square, yes, omega 0 square minus lambda square root over. Okay. So, that is the omega d, and this is the case for underdamped motion where you can still find an oscillatory motion due to this function, but the amplitude is exponentially now decreasing with time, and that is why this is no longer a periodic motion. That means just after some 2 pi angle or 2 pi phase, the displacement is not exactly the same. Okay. So, then we talked about the overdamped oscillation, and overdamped oscillation is just a superposition of two exponentially decaying functions. So, it should be exactly here x t is equal to some a e to the power minus lambda minus root over lambda square minus omega times t plus b e to the power minus lambda plus root over lambda square minus omega square times t. Okay. And finally, I had this critically damped situation where lambda and omega 0 they are equal, and for that we said that the correct equation should be correct solution should be a t x t will be equal to some a plus b t, okay, times e to the power. I have to just check the symbols, was lambda t. Okay, so I call them this thing, yeah, the symbols are okay. I just use the same b e to the power minus lambda t, because you see that at this case, okay, your lambda square minus omega 0 square is vanished. So, you do not have a contribution from that part and you have simply like this. Now, you see, since you have this lambda is equal to omega 0 in this part, you will have a plus b t times e to the minus omega 0 t as well. Okay. Now, I asked you a question at the very end of the last lecture that which one. So, we also argued that unlike this one, these two have no oscillatory part at all, okay, only decreasing part, but the question was which one of them is decreasing the quickest. Okay. So, today I will actually compare all these three and I will show that this one is the one which decreases the quickest. Okay. Why? So, let me just draw some plot over here. Okay. And so, here I am just plotting t and here I am plotting x as a function of t. So, I am just now in order to compare, I am just like adjusting the initial conditions so that at t is equal to 0, everyone is having the same displacement. Okay. So, then I can actually say for underdamped case, I will just use three colors. So, for underdamped case, I take the light blue color. So, you know that there is an envelope like this, exponentially decaying envelope, and the oscillatory part is actually modulated by this. So, this is the cosine part, okay, and this envelope actually determines the nature of the decreasing of this function, and this is given by something which is proportional to, okay, I should not confuse between alpha and proportional, okay, something let us say some, as I wrote here, a e to the power minus lambda t. So, it should be minus lambda t. Now, you see here in this case lambda is less than omega 0. So, of course, I can say that it will with the same initial condition, okay, this curve is always less steep than a e to the power minus omega 0 t, because omega 0 in this case is greater than lambda. So, when there is a minus sign, so this one will actually decrease much quickly, much quicker than this one. Okay. So, and that is why you will have a less steep decrease than this one. What about the overdamped case? So, for overdamped case, we also know that there will be simply there is no oscillatory part like this, but there will simply be parts like this. So, something like this. Okay. Now, the question is this also less than or greater than omega 0 t? Okay. Now, here the mathematics is a little bit more tricky. We have for overdamped case, lambda greater than omega 0, okay, and I can actually write that lambda plus omega 0 is less than lambda minus omega 0, that I can always write, okay, because all of them are positive. Okay. So, that is completely okay, and then I can also write these, the square roots. Now, I multiply both sides by root over lambda minus omega 0. So, in this side you will have lambda plus omega 0 times lambda minus omega 0 whole root is greater than lambda minus omega 0 whole square. Now, you see the sign here does not change only because lambda is greater than omega 0, and so you are actually multiplying both sides, okay, by a quantity which is positive. Okay. So, that is why this sign does not change over here, although I should not keep this. And if you have this, finally you can say, okay, root over lambda square minus omega 0 square will be greater than lambda minus omega 0. Okay. And then finally you can say, okay, my lambda minus, so I just take this one in this side to this side and this one to this side. So, lambda minus root over lambda square minus omega 0 square should be less than omega 0. So, that is a very important conclusion in this case, and that is why I can say, so again if you just go to check this solution, you will see that this solution has two parts, one is multiplied with A and another is multiplied with B. Now, this part which is much more greater than lambda, okay, it falls off very quickly. So, the term which actually survives and which can be compared to the surviving part of the other underdamped and critically damped oscillation is this part, the first one. And this first one we have shown that this thing, this lambda minus lambda square minus omega 0 square is actually again less than omega 0. And so, I mean again this e to the minus lambda minus root over lambda square minus omega 0 square t is less steeper than e to the power minus omega 0 t. Okay. That we can always say. That means, this one is decreasing much quickly. Okay. Finally, when you have this critically damped motion, then for the first time you have lambda is equal to omega 0 and omega 0 for an oscillator is somehow fixed. This is independent, this is fixed for an oscillator, the natural frequency is fixed by the property of the source. This is independent of the medium's viscosity, this is also independent of the nature of the forcing. Omega 0 is actually coming due to the nature of the oscillator itself. For example, when we are just imagining an oscillator made up of spring, then omega 0 is nothing but root over k by m. So, this is actually given by the stiffness of the spring and the mass of the oscillator particle, and there is no effect of the external force and the medium. Okay. So, once you fix your oscillator, its natural frequency is actually fixed. Okay. And that is why for critically damped case, you have for the first time a damping rate which is exactly proportional to e to the power minus omega 0 t, and that is why, and for for large value this part actually does not dominate. So, this part dominates. So, for large value we will always have like this. Sorry, the drawing was not perfect, but I can simply draw this. Yeah. So, you see this is the critically damped motion. So, what we have seen that it is a little bit counterintuitive, but critically damped motion damps much more quickly than even over damped motion. Under damped motion we can even forget now. Okay. Even from with respect to over damped motion, critically damped motion decays much more quickly. Okay. And that property is used in the case of when we are making some sound absorbing walls in the studios, and whenever we want to make a wall which absorbs shocks and other unwanted phenomena, then we want this type of decaying to be very, very quick or as quick as possible. Okay. So, that is why then we have to smartly choose the omega 0 to be equal to the lambda, and lambda is something which is, now you understand, is depending on the medium, because this is given by the medium's viscosity. Once again, if you remember this case, this lambda is equal to omega 0, there is actually no forcing here. Okay, there is no effect of forcing, this is just a damped harmonic oscillator. This is a simplified model. Today we will see with the appearance of a force how it changes, or really it changes or not, but that is not a very problem over here. Okay. So, what we can say that if this is the competition between the lambda and omega 0, and now you have to understand the medium properly, and from your knowledge or using your knowledge, you first have to calculate or give a value, estimate a value for the damping coefficient for the medium, and then you have to now play with making a equality, okay, to adjust or tune the oscillator in such a way that its omega 0 exactly is equal to lambda. Okay. Or you can say that if my oscillator is already given, some oscillation has already taken place, then I have to now choose a medium smartly, and that is the fabrication part, so that its lambda is exactly equal to omega 0. So, this is the two ways of approaching the same problem. Okay. So, in the next subpart of this lecture, I will actually start the discussion on an oscillator with both damping and forcing. Thank you.